So this is the second part of the Michael reaction, and it's called stoic enamine reaction, and you'll see the relationship as to why it's under Michael addition. But to put it in a context, so far, what we've looked at is that the enolate and enol. Sorry, go through that. Enolate and enol. You know, I'm going to rewrite it again. Enolate and enol. They served as our nucleophile. And what we did was we took the enolate and enol and varied the electrophile. So the electrophile that was used, for example, halogenation. We looked at alkylation with the alkyl halide. We looked at aldehyde and ketone for aldol. So the carbonyl served as an electrophile. We looked at esters in Claisen. And lastly, we looked at alpha beta saturated in Michael. All right, so we looked at all these different electrophiles, but one thing that was common was that the enolate or enol always served as our nucleophile. So and all the reactions that we went through, if you go back, we did the halogenation, we did the alkylation, we did the aldol, we did the Claisen, and we did the Michael, right? So what we're going to vary now is we're going to look at one other nucleophile. And the nucleophile that we're going to look at are enamines. All right. Now, I hope you remember what enamines look like. This is from Unit 2, in which you took an aldehyde or ketone with the secondary amine and with acid catalyst, or no, we needed a, with the two equivalents of this and an equivalent of acid, we made enamine. And it's an equilibrium process in which when you remove water, you get your enamine as your product. All right, so this is enamine, and what I want you to look at is compare this with enolate or enol. So take a look at enamines. Versus enol, and really the difference between enol and the enolate is that you have a negative charge, but okay, so enol and enolate were our nucleophiles, and if you look at it carefully, notice the similarity between the enamine and especially enol, because they're both neutral and this is negatively charged. But notice where the double bond is. Notice that there is a lone pair on the nitrogen, just like on the oxygen. And so enamines, because they're structurally similar looking to enols, they could serve as nucleophile. All right. So for example, how it could do that is shown by this right here, where the lone pair on the nitrogen is used to reform the double bond between the carbon and the nitrogen, and then the double bond is used to have the negative charge on this carbon, which would be the carbon next to it. And here you're making a ammonium salt. So So notice this now versus enolate, which would look like this, right? If it was the same compound, right? So notice how this resonance structure of the enamine looks very much like the enolate and the enol. All right, so this carbon right here, where the negative charge is where the nucleophilic centers could be, just like in enolate and enol, the carbon next to double one O was the nucleophilic center. So what this means is that this could go and react with an electrophile and put the electrophile on to the beta carbon, to the alpha carbon, and then this ammonium salt, as you know, readily hydrolyzes with water, and basically you get your carbonyl back with electrophile attached to it. So your question might be, why bother with making the enamine and then do the electrophile? Because, why not go straight from the enolate and go straight to so why not go from enolate to the product of adding the electrophile? And the reason for using enamine rather than the direct enolate is because enolates are not good microdonors. All right, so remember when we talked about Michael reaction in the last lecture, so the only enolates that work are the ones that are with a double electron withdrawing group, and the ones that are normal enolates do not work as good microdonors. So if we wanted to do Michael reaction, this won't work. So if I want to, for example, take this and react with the LDA and to make the enolate, and then react with this electrophile, the Michael acceptor, and then quench it, and I want to get, my goal is to get, so you have a negative charge here, react over at the beta carbon, so then you would have this, which is 1, 2, 3, 4, 1, 5 dicarbonyl. So if I make the enolate of this, because it's not doubly with the electron withdrawal group, it does not do the second step. So this product that you desire is not obtained, or it's going to be obtained in very poor yield. All right, so this is not an option. But if you did the enamine chemistry, so instead of directly reacting with LDA, you take this and react with secondary amine and made the enamine first. All right, enamines, remember I said we're going to go over this. Enamines are good microdonors. So after you make the enamine, then you could react with the Michael acceptor and then quench it, and then what you're going to have is have the reaction go, and this hydrolysis is going to hydrolyze the ammonium intermediate. So you're going to get your carbonyl back. So then you will definitely then will have, so 1, 2, 1, 2. So then you will have 1,5-dicarbonyl in good yield. All right. So even though the way you want to do it, which is this, start directly from the ketone and react with the base, and then and then the microacceptor, this does not work. So basically this is not an option. So if you wanted to make 1,5-dicarbonyls using a ketone, then you have to go through the enamine as an intermediate and then do the micro addition and then hydrolyze it. All right, so that's why this reaction is very useful. And this reaction that we just wrote out, it's got a special name called Stork enamine addition reaction. So because this is actually used a lot in synthesis. All right, so that is the advantage of using enamines. And here what is shown is that the enamines can not only be used with a micro acceptors, but it could also be acylated. So here's an example of an acylation as an electrophile. So here the enamine is acting as a nucleophile, and you know where it will react. This should be very easy for you to understand. And then once you get the ammonium salt, then you hydrolyze it and you get your ketone back as the product. Okay, so here's an example of an acid chloride as the electrophile, and this is same example that you've seen. So you should be able to give me the product of this. But not only that, alkylated, if you react with an alkyl halide, you could do the same reaction as well. Okay, and this reaction is actually used in something called Robinson annulation reaction, which is how chemists make a 6-member ring very easily. And all this is a sequence of a one-pot reaction. So it makes it really easy because you do everything in one pot. So you do the you make the enolate with the base, and then because it's doubly electron withdrawing group enolate, it's going to readily do the micro reaction. And when you do the micro reaction, you get this intermediate for this reaction. And I'm gonna, it forms the enol, which is gonna tautomerize to the ketone form. And notice here, you have all kinds of carbonyls here. So what happens is then an intramolecular aldyl condensation occurs. So this is intra, in where 6-member ring forms because that's more stable. So if you put a negative charge, make an enolate here, and then attack one of these carbonyls, you'll see that you form. So when you do that, I'm gonna draw this. So the carbon-carbon bond formation occurs, right? And then this is OA, O minus. And then if you take this and it gets pronated as an OH, and then it's removed as water, and you form basically, if you draw prettily, you form alpha beta unsaturated ketone, because this OH will leave as water and form a double bond between this carbon and this carbon. Okay, so this is how you make a 6-member ring. So you should be able to do these draw problems as well as 22.47a and 22.49.